Hello. Hello, everyone. Very excited to be here. And my name is Yotam from the University of Tokyo. And on behalf of my co-authors, I'm happy to present VeasyGuide. So online learning is very common these days, especially with videos in platforms like YouTube, Khan Academy, Coursera, or even recorded lectures from Zoom. And many of these videos also contain slides. And for learning, communication between instructors and students is very important. And how do instructors communicate with students in slide-based videos? So a lot of instructors use, for example, pointers or digital pens to communicate their intent to the students. For instance, instructors can use pointing actions to point to different parts of the slide to convey their intent, or they can use marking actions to emphasize certain portions of the slides. Moreover, they can use sketching to add additional content to the slide and explain different concepts to students. So using these three methods, pointing, marking, and sketching, instructors can communicate with the students. Let's see an example of that from Khan Academy. Try to pay attention to the pointing, marking, and sketching actions, and this video has sound.
All of our elements are listed here in the periodic table of elements. C stands for carbon. I'm just going through the ones that are very relevant to humanity, but over time you'll probably familiarize yourself with all of these. This is oxygen. This is nitrogen. This is silicon. This is Au is gold. This is lead.
As you can see, trying to follow along is kind of challenging, and it can be very difficult, especially for low vision learners who still use their residual vision. So for low vision learners, this kind of like problem is called the visual search problem, which is basically not knowing where to look and what to look for. And this leads to a lot of like frustration, exhaustion, and very high cognitive effort, which makes learning a bit much more difficult. So a lot of people just give up on the visuals and only listen, but they give up on a lot of visual information that can be very important. So this poses our main research question, which is, what can we do to improve this experience for low vision individuals? And to address this, we introduced VeasyGuide. So VeasyGuide basically detects activities such as that, highlights them, and makes it simple to zoom with personalization incorporated. Now I'm going to show the same video as before, but with VeasyGuide enabled. The users can click to zoom, or they can pause the video to personalize the highlights.
All of our elements are listed here in the periodic table of elements. C stands for carbon. I'm just going through the ones that are very relevant to humanity, but over time you'll probably familiarize.
And the user can personalize as well.
Yourself with all of these. This is oxygen. This is nitrogen. This is silicon.
Or change the personalization.
This is Au is gold. This is lead.
So VeasyGuide was created in a co-design process. It was a co-design with 3 low vision participants, as well as my own experience as a low vision individual. And we had 3 main questions for the co-design process. The first is, how do low vision experience visual activities? What challenges these activities introduce? And also, what makes these activities easier to detect? For the sake of time, I'm going to focus on the third question. So through the co-design process and the iteration, we created those design implications for VeasyGuide and ones that VeasyGuide is based on. The first one is, of course, providing visual access with less effort. And we do that through highlights and magnification or zoom. The second one is that visual styles should be familiar to users. And familiarity is something that we achieve through consistent styles throughout the video, and also using familiar indicators. So for instance, in VeasyGuide, we use mouse pointers of different shapes. One more thing is predictability of what, when, and where to look. So in VeasyGuide, we introduce a 1.5 seconds pre-activity highlight. So the highlight shows before an activity starts, and also we implement a box shape highlight, which C1 mentioned. The box tells me exactly where and on what to look at. So the box gives spatial information as well. And finally, personalization for different visual abilities. So different people have different needs. And so having personalizations as part of the design itself allows VeasyGuide to be usable by many more people. So these are the 4 design implications that are the source of VeasyGuide. VeasyGuide itself is composed of 2 main components: an activity recognition pipeline, which uses computer vision methods, as well as a graph representation of visual changes that allows us to detect activities, and activity visualization, which is implemented as a web-based application, so activities can be changed and customized on the fly. And this is the base of VeasyGuide. This is how VeasyGuide works. So getting back to our research question of how can we improve it. So the question is, will VeasyGuide improve the experience of low vision people? So to evaluate VeasyGuide, we used real-world videos from various creators with various styles. And we had recruited 8 low vision participants to basically try and see if it can improve low vision access to visual activities. But more than that, we also recruited 8 sighted participants to see what will be the impact of VeasyGuide on sighted people. And we had 2 main tasks. The first is a localization task, which allows us to focus on the visual search problem specifically. And the second task is a viewing task, which allows us to explore the experience of learning with VeasyGuide. So in this work, we prioritize external validity. So we allow participants to use any of their assistive tools, such as magnifiers, screen readers, etc. And here are some of the results. So the first thing is that VeasyGuide significantly allows low vision people to notice more activities. So from a 16.9% accuracy, we go up to 88.2%. So this is a significant improvement. And they do that with faster times. So we have a median of 1.37 seconds using the baseline, so no VeasyGuide, compared to 1.19 seconds with VeasyGuide. So we can make it faster as well. But more than that, VeasyGuide also significantly reduced the cognitive load that is needed for learning. So on all of the cognitive load metrics that we tested, effort, frustration, mental demand, physical demand, and temporal demand, VeasyGuide reduced significantly the difficulty there. And more than that, qualitative findings support our results. So VeasyGuide makes it easier to follow along the instructor. L2 mentioned, I felt as if the instructor had control, so I can connect with the instructor's intent. And L3 mentioned, it helped me stay with the instructor. I saw that the instructor was drawing a boat, and I was happy I did not miss it. VeasyGuide also improved the overall experience of learning. L1 mentioned, one of the biggest problems is that I don't know what in the video requires my attention. VeasyGuide offloads this difficulty to software, and I strain less. L5 mentioned, I felt relaxed listening instead of constantly worrying about where the next thing would show up. I could just sit back, listen, and learn, and remember why I enjoy learning. But of course, VeasyGuide contains some limitations as well. First of all, the learning curve. So VeasyGuide has some learning curves to it. L1 mentioned, I would have to get used to it, but getting used to it and figuring out my own workflow would let me, I think, worry less about the visual part and focus more on the content. And some users wanted more granular control. So beyond the personalization, some users wanted more control. So L6 mentioned, with a zoom, parts of the screen get cut off, so I might have missed things. I'm not sure if there was a way to move the zoom window, but I'd really like the freedom to move it around. So beyond what we did with personalization, some participants wanted extra controls as well. For sighted participants, we found that VeasyGuide provides some benefits as well. For example, it helps retain and preserve attention. So S1 mentioned, if I'm bored, the highlights help draw my attention back to the video and to the right place. It also helps focusing on the learning, with S2 mentioning, I could just focus on receiving information. It allowed me to focus on the learning part. So beyond low vision people, VeasyGuide also has the potential to enhance the learning experience for others as well. To conclude, we discuss in the paper on how can we design tools to support low vision users in tasks that require visual search. So we reflect on our findings from the co-design process as well as the user study. And we found 4 key concepts as a design framework. The first one is familiarity with target visuals. The second is predictability via spatial temporal context and personalization for changing needs. So all of these are extended beyond the co-design findings. And we introduce another one, which is preserving user agency, which I want to explain on in a little bit more detail. So VeasyGuide basically gives low vision learners the choice to look, see, or follow the instructor. And with VeasyGuide, they have the freedom to always find the right place of focus. So they can look anywhere else in the slide and decide, actually, I want to see what the instructor is talking about now. So it gave them the option, similar to some people, to basically see whatever they want to see at a time and not miss out on things. Thank you so much for listening. I'm very excited to share this work. VeasyGuide is available online right now with a few sample videos, but very soon you will be able to use your own videos and have VeasyGuide work on them. So please stay tuned for that, and thank you so much.